All right, this is Business Calculus section 5.3, part 2, and we're going to continue on with finding the area under curves. So the fundamental theorem of integral calculus shows how to evaluate definite integrals by using indefinite integrals. Okay, so we're going to find for a continuous function f on an interval from a to b, we're going to be able to integrate from a to b a function. So f of x dx is going to be equal to f of b, capital F of b, minus f of a, where f is any antiderivative of f. So what we're going to do is we're going to take a function, integrate it. So I'm going to integrate a function from a to b of f of x dx. Once I integrate that function, we're going to turn it to a capital F of x, and we're going to evaluate it from a to b, which is just capital F of b minus capital F of a. When we do this, when we actually apply this fundamental theorem of integral calculus, or just the fundamental theorem of calculus, sometimes you'll see that written as FTC. We don't add the plus c. Okay, we're going to ignore that part and just deal with the numbers that come up as we integrate the function. So, the theorem is fundamental in that it establishes a deep and unexpected connection between the definite integrals, which is those limits of Riemann sums, and antiderivatives. It says that definite integrals can be evaluated in two simple steps. 1, find the indefinite integral of the function, omitting the plus c. And 2, evaluate the result at b and subtract the evaluation at a. Okay, so this is what's going to happen. We're going to find the integral and then evaluate. That's going to work every single time, and the result will be the area under the curve for that function. And we're going to go back to the function we started with, the area under the curve of x squared from 1 to 2. So when we integrate from 1 to 2 x squared dx, remember the integral of x squared would be 1 over 3 x cubed. We're going back to that, the integral of x to the n dx is 1 over n plus 1 x to the n plus 1, that power rule that we learned back in section 5.1. And again, we're getting rid of the plus c for this step. We're now going to evaluate that function from 1 to 2. So I've got 1/3 times 2 cubed minus 1/3 times 1 cubed. So 2 cubed is 8 times 1/3 is 8/3 minus 1 cubed is 1 times 1/3 is 1/3, giving us 7/3, which reduces to, or simplifies down to 2.33. And that is the answer that we ended up coming up with in that very first example. And you're done, that's it. All right, so I want you to pause the video and find the area under the curve y equals x cubed from 0 to 2. And we're going to evaluate from 0 to 2 x cubed dx. I left my dx off up here. Okay? Okay, so when you find the integral of x cubed, you should get 1 over 4x to the 4th, and we're going to evaluate that from 0 to 2. So I've got 1/4 times 2 to the 4th power minus 1/4 times 0 to the 4th power. I'll put a 2 there, sorry. And we end up with 16 over 4 minus 0, which is 4. So that first step of finding the integral from here to here is exactly the same as what we've been doing since section 1 of this chapter. That doesn't change at all. The only new step is as we move forward, evaluating at the given limits. All right, let's keep going. All right, so we've got two more examples. We want to find the area under the curve of y equals e to the 2x, evaluated from 0 to 1, and then also the area under the curve from 1 over x, evaluated from 1 to e. So the first one, anytime it says find the area, that's your hint that we need to find an integral. So I'm going to integrate from 0 to 1 of e to the 2x dx. When we find the integral of that, remember we do 1 over the coefficient of x, so 1 over 2 e to the 2x. We're going to evaluate that from 0 to 1. So when we plug 1 in, I've got 1/2 times e to the 2 times 1 minus 1/2 times e to the 2 times 0. All right, so I have 1/2 times e squared minus, remember that anything to the 0 power is 1, so that goes away, leaving us with just minus 1/2. And you can leave it right here. This would be the exact answer, because once you plug that in the calculator, you'd have a decimal. So here's your exact answer. You can leave it exactly like this. If you may also see it sometimes on standardized tests where they factor out that 1/2, leaving you with e squared minus 1. Or you'll see it as a decimal and you can plug that in your calculator. But either way, okay, this first step here would be perfectly fine. Okay, that's simplified as far as you can go, and that'd be a fine way to leave your answer. Now let's try the next one. Finding the area under f of x equals 1 over x. And this is evaluated from 1 to e. So we're going to find the integral from 1 to e of 1 over x dx. If you recall from section 2, 1 over x dx is ln of x. We're going to evaluate that from 1 to e. So when we plug in, we have ln of e minus ln of 1. All right, if you recall, ln of e is just equal to 1, and ln of 1 is 0. So all of this simplifies to 1. The integral under that, the area under the curve from 1 to e would just be 1. Now, the next part gives us some rules that we can follow. So definite integrals have many of the properties of indefinite integrals, and these properties follow from interpreting definite integrals as limits of Riemann sums. So the same rules that we learned in section 5.1 apply. If you have a constant inside an integral, you can pull it out to the front and then integrate. Also, if you have a plus or minus sign separating two individual functions, you can break it apart and find two different integrals. You don't have to do that step. You can integrate just taking one step at a time, that's fine. Or you could separate it out first and then integrate. Wouldn't matter either way. So let's do another one. We want to find the area under the curve of y equals 24 minus 6x squared from -1 to 1. If we look at this graph from -1 to 1, we can see that all of it is non-negative. Okay, so we can find the integral from -1 to 1 very quickly. It's very important that you would plug these into a calculator. I hadn't shown that yet. That you would plug those into a calculator and make sure that your graphs are non-negative. If you have a part that's not non-negative, that's not positive, there's an extra step involved. Okay? So if we're finding the area for this one, it's all positive, so we're good. We're going to integrate from -1 to 1 of 24 minus 6x squared dx. All right, so when we integrate, the integral of 24 would just be 24x. The integral of 6x squared would be 6 over 3x x cubed. And then again, all of that is evaluated from -1 to 1. Right, when I plug in my numbers, I've got 24. So here's the first part, 24 times 1 minus, I'm going to go ahead and put 2 for 6 divided by 3. 1 cubed. So all of this is just the first number. Then we have to subtract and plug in our second number. So 24 times -1 minus 2 times -1 cubed. Okay, sometimes when you have more than one term inside your function, it's easy to forget to subtract off that second part. So I like to put it in brackets just so I remember that I've not, or just so I can check that I haven't missed any part of the function. All right, and then we're going to simplify. So we have 24 minus 2 minus a -24, so plus 24, and then minus a +2, so minus 2. If you plug all that together, we end up with 44. And you're done. All right, so I'm going to finish out this section on one more video.